Let us see the oxyacids of phosphorus. Phosphorus forms many oxyacids. The first in the list is H3PO2. It's called hypophosphorus acid. In this case, the structure is, remember, all its oxyacids basically are sp3 hybridized. They will be having tetrahedral structure. And in this, the structure is like this. There is one OH group and the two H are directly bonded to phosphorus. That is why its N factor or its basicity is only 1. It's not 3 as it appears from the formula. It's 1. The second acid is H3PO3, which is called phosphorus acid. Now, in this case, what we find is there is one double bonded oxygen, of course, which will be there in all phosphorus oxyacids. And then there are two OH groups with one H directly bonded to phosphorus. So this H will not come out like in this case is. And since only these two H will come out, the N factor or the basicity of this acid is 2, not 3, again as it appears. Third acid in this category is H3PO4. It's called phosphoric acid. In this case, of course, after forming a double bonded oxygen, there are 3 OH group. So the N factor or basicity of this acid is 3. Now this phosphorus acid, when heated, its 2 units combines with each other and it forms what? The double unit of this, which is called pyrophosphorus acid. Pyrophosphorus acid is H. When you double this, it becomes what? 6. So it becomes a H4, P2O5. So that's called pyrophosphorus acid. Pyrophosphorus acid. In this, what we find is, of course, there are two phosphorus like this. There are two phosphorus which are joined to each other through a common oxygen. They both are having double bonded oxygen. And there are 2 OH group, one on each one with each phosphorus, and there are 2 hydrogen directly bonded to one with each phosphorus. So this is your pyrophosphorus acid. Similarly, we have the double of this. When this acid is heated, one water molecule is lost, and the double of this acid is H4. It becomes 4 P2O7. It's called pyrophosphoric acid. It's called pyrophosphoric acid. In pyrophosphoric acid, what we find is we have this structure. So it's H4P2O7, pyrophosphoric acid. Now this metaphosphoric acid exists in different, mainly in 2 different types of structures. It forms cyclic as well as linear polymeric structures. Let me give an idea. Like when this phosphorus oxyacid is present like this, like in this form, this is its one unit HPO3, then from here to here one HPO3. We call it polymetaphosphoric phosphoric acid, in which what we can see is that it is existing in the form of a long polymeric chain like usual polymers. So it's called polymetaphosphoric acid. In a very similar way, what we find is if it is forming a cyclic structure like this one, in which we have a double bonded OH, double bonded oxygen OH, double bonded oxygen OH, double bonded oxygen and OH. What we find is, again from here to here, this is one unit. So we will call this as HPO3-4. So there are 4 units of this metaphosphoric acid combining with each other to form a cyclic structure, which is called cyclo-tetra-metaphosphoric acid. So this is what, these are the basic oxyacids of phosphoric acid. Now, important property of the oxyacids of phosphorus. The oxyacids of phosphorus which are existing in +3 state like this one, H3PO3, which is called phosphorus acid, in which phosphorus is present in +3 state. When heated, they shows disproportionate reaction, which shows that they are not very stable, and it forms phosphoric acid, H3PO4 and phosphine, where it get oxidized to +5 and reduced to -3. Another important thing, those oxyacids like H3PO2 and H3PO3, which are having pH bonds in them, they can be used as a good reducing agents because they can give out that hydrogen. That is why when silver nitrate solution is treated with hypophosphorus acid, silver nitrate gets reduced to silver, and what we get is nitric acid formed along with phosphoric acid. So this is what this reaction shows, that these oxyacids, the two out of which this is better one, can be the good reducing agents also.